Welcome back. In this tutorial we are looking at an example of looking for the MGF. So let x be a random variable with PDF f of x being the lambda times exponential of negative lambda x, where x is greater than 0. So it means that x here ranges from 0 all the way to infinity, then 0 elsewhere. So the task here is to find the MGF, that is the first task, if it exists. Then the next task is to derive the expected value of x. Expected value of x is same as the first row moment. And next we look for the variance of x from the MGF. Then the last case is to verify the results by computing the above quantities directly from the definition. So let's begin with the first step, looking for the MGF. And by definition, we know that the MGF, which is mx a function of t, is the expectation of exponential of tx. And since here we are dealing with a continuous random variable, then this is same as the integral of the product between exponential of tx and f of x, which is the PDF, and we integrate it with respect to x from negative infinity to positive infinity. Remember, negative infinity to positive infinity are the limits of x in this function, and in the given function f of x, you can see x is greater than 0, which means that it ranges from 0 all the way to infinity. So we are going to substitute f of x, and then we also substitute the limits, and therefore we are going to have the MGF being given by the integral of exponential of tx times lambda times exponential of negative lambda x. We integrate it with respect to x from 0 to infinity. So what we are going to do, we are going to collect the exponentials together, and therefore using the laws of indices which we learned, we are going to rewrite this as the integral of lambda exponential of tx minus lambda x, and you integrate it with respect to x from 0 to infinity. Next, we are going to factor out lambda, and also in this exponential we are going to factor out negative lambda x because it is common, and therefore we are going to have lambda into the integral of exponential of, in the first term when we factor out negative lambda x, then we are going to remain with a negative t, which is this one here. Then in the second term we have negative lambda x. When we factor out negative x, we are going to remain with positive lambda, and therefore we'll have lambda into the integral of exponential of negative into lambda minus t times x, and you integrate with respect to x from 0 to infinity. So remember, we have factored out negative x, so I've just written the negative just before the bracket and the x after the bracket. So with that, the next step is to do the integration. And in our previous classes, we were able to review on how we can integrate exponentials. And we said when you are integrating exponentials, what you need to do is to take the original exponential, divide by the derivative of the power of that exponential. So our original exponential is exponential of negative lambda, negative into lambda minus t times x. So we are going to have lambda, which we had factored out, then times exponential of negative into bracket lambda minus t, you close the bracket x. Then next we divide by the derivative of that power of the exponential, and you can see here we are, remember, we are differentiating with respect to x. So negative into lambda minus t in terms of x is like a constant. So what we'll be differentiating here is x with respect to x, and when you differentiate x with respect to x, you are going to get 1, and therefore you are going to remain with negative into lambda minus t. So that is what you are going to divide the original exponential with. Then we apply the limits, which is from 0 to infinity. And as we apply the limits, we can do away with the constants, we factor them, and then we just deal with the exponential, which is the one which is involving x. So when we factor out lambda over negative into lambda minus t, which can also be written as lambda over t minus lambda, then we are going now to apply the limits where there is x we are going to apply the limits. From the upper limit is infinity, so we have exponential of negative into lambda minus t, you close the bracket, times infinity, and this one reduces to exponential of negative infinity. Then minus, we apply the limits, the lower limit, which is 0, where there is x we put 0, so we are going to have exponential of 0. So exponential of negative infinity can be written as 1 over exponential of infinity. So exponential of negative infinity can be written as 1 over infinity, that is from 1 over exponential of infinity, from the in laws of indices. And this can also be written as, since this is exponential of infinity, this is just but 1 over infinity, and 1 over infinity we know that is same as 0, so this one reduces to 0, so the first term here becomes 0. Then minus exponential of 0 is 1. So you can see here we'll have 0 minus 1, which is negative 1, which reduces to, if we multiply by whatever is also the bracket, we'll have negative lambda over t minus lambda, which can also be rewritten as lambda over lambda minus t, which can also be rewritten as lambda into lambda minus t raised to negative 1, which is the MGF of the random variable x. So that's how simple we can find the MGF. We move to the next part, that is B. We are required to derive the expected value of x. And we know that the expected value of x is same as the expectation of x, which is the first raw moment. And we said that the first raw moment is obtained by differentiating the MGF once with respect to t, and then setting t to be equal to 0. So since our MGF is lambda over lambda minus t, which can also be written like this, then we are going to differentiate these on respect to t. The first term here is a constant, it does not deal with t. Then here we have, inside this bracket we have t. So what we are going to do, we are going to begin by letting whatever is inside this bracket to be u. So we are going to have u raised to negative 1. So we are going to differentiate u with the raised to negative 1 with respect to u, which you are going to get a negative 1 times u raised to, we reduce the power of u by 1, so it will be raised to negative 2. But what is u? Our u we have said is lambda minus t, and therefore we substitute u with the lambda minus t, and you can see we are going to have a lambda minus t raised to negative 2. Then there is this negative 1. Then now next we now differentiate the u itself. Remember, the u itself is lambda minus t. So we want to differentiate u with respect to t. This is a constant. So when you differentiate a constant with respect to t, it will be 0. Then we have negative t. When you differentiate this one with respect to t, it will be the same as negative 1, which is this one here. So you can see now the next step is to simplify. Negative 1 times negative 1, it will be positive, and therefore we are going to have lambda times into bracket lambda minus t raised to 2. So this is the first derivative of the MGF, which can also be written like this. The next step is to set t to be equal to 0. So where there is t, we put 0, and you can see t is here. So when you set t to be equal to 0, we are going to have lambda over lambda squared, which simplifies to 1 over lambda, and therefore this is the expectation of x. The next part is to find the variance, and we are going to use the definition of variance. We know that when we were dealing with variance, we were able to come up with two formulas for finding variance, and one of the formula is that variance of x is given by expectation of x squared minus the square of expectation of x. Expectation of x squared is the second raw moment. Then expectation of x here is the first raw moment, which we have already obtained it to be 1 over lambda. So for the second term here, we just need to replace 1 over lambda in this bracket, and then we square. Then it means that we need to find the second raw moment, and the second raw moment is obtained by differentiating the MGF twice with respect to t, and then setting t to be equal to 0. So from here, we are going to differentiate the MGF once more with respect to t. So lambda here is a constant. So a constant is not affected by the derivative because we are multiplying by uh, a function of that variable. So this one can be factored outside. So we are going to have lambda. So what we need to do is to differentiate this part here. And since we have a bracket here and inside it we have our factor, our variable, which is t, we are going to let this one to be maybe z. So if you let z to be lambda minus t, then you are going to have z raised to negative 2. So we first of all differentiate z raised to negative 2 with respect to z, and this will give us negative 2 times the power of z now will be reduced by 1. It will be the same as negative 3. But what we know, z we have said is same as lambda minus t. So you can see here we are going to have lambda minus t raised to negative 3. Next, we differentiate the z itself with respect to t. And remember, z we have said here is same as lambda minus t. And when you differentiate z here with respect to t, this is a constant. When you differentiate it with respect to t, it will be 0. Then negative t, when you differentiate it with respect to t, it will be negative 1. So here we are going to multiply by negative 1. So we are going to have lambda times negative 2 times the lambda minus t raised to negative 3 times negative 1. So this negative and this negative here will become positive. So we are going to have twice lambda into lambda minus t raised to negative 3, like that. And this one can also be written as twice lambda divided by lambda minus t cubed. The next step is to set t to be equal to 0. When you set t to be equal to 0, you remain with twice of lambda over lambda cubed, which reduces to 2 over lambda squared. So next, we are going to substitute in our formula for variance. So where there is expectation of x squared, we put 2 over lambda squared. Where there is expectation of x, we put 1 over lambda. And when you simplify, you'll get 2 over lambda squared minus 1 over lambda squared, which simplifies to 1 over lambda squared, which is the variance of x. Then the last part of that problem, we are required to verify the results by computing the above quantities directly from the definition. So here, I'm not going to go through this one here, but at our own time, you are going to compute directly from the definition, that is using the expectation, as we did in our previous classes. And what you are going to see is that you are going to get the same results as seen in part B. So if you look at your notes, I've proven that one, but I want you to do it by yourself. But what you are going to notice is that the two solutions will be the same as the ones which you have obtained in part B above. With that, I am now comfortable that you have understood how to use the MGF to find the moments. Thank you.